morning, everyone. Thank you for coming. And yeah, today I'm going to share my experience how I was building my own JVM programming language. It's a toy programming language. And I will tell you about how I came to this thought, why did I decide to build it, and what tools did I use to build it. And then I'll also show you some demos in the end to prove that it actually works. Actually, my story starts, I think, at some conference when I was listening to people saying when they learn a new JVM programming language that they don't know yet, they would look into the bytecode and see what it does inside. And I was a bit curious because I don't do that. And I actually, in fact, didn't really know how the bytecode looks. So I was curious, and I came home, and I looked at the bytecode, and I saw this. So to see the bytecode, you can run a simple command, javap -c, and some class name. So I created a very simple class, and I looked at this. And of course, here you can see that some class definition, right? You can see the constructor inside. You can see the main method definition. And inside, you can see something is happening. There are some operations, but it is really hard to intuitively guess what they mean if you don't really know. And there are some explanations that try to help us out, but it's still a bit tricky if you don't know what it is. And that got me even more curious, so I decided, okay, let's dig a bit, how does it work? And then I was already thinking, okay, maybe I can also try to generate the bytecode so I can understand it better. And this wasn't already very far from actually building a toy programming language. So why did I do this? I wanted to understand how the bytecode works. I wanted to understand how the JVM languages work internally. And it is a lot of fun. It was a lot of fun to build this language. And I actually finished this project in the end. And as a bonus, now I'm able to build any other DSL, and it can be very useful for regular job at the client or whatever. So I decided, okay, if I build a programming language, let's give it at least some purpose. So let it be useful for somebody. So my idea was, let it be a language for people who are not very technical, so they can maybe intuitively use it. Let it be the language that doesn't look like other JVM languages, so it doesn't look like Java with just more sugar. So it will be something completely different. And I would add some different ways to express the same thing, so people, non-technical people who will use it, they can intuitively try things and it will just magically work. I thought I'd use human words that would be forming normal, regular human sentences. So it came as far as I even sometimes the symbols like plus and minus, I would be also giving a possibility to word it with words just for fun, why not? And I thought, okay, let's also support a bit of programming style sometimes, so it's actually usable by developers as well. And I decided to give it a name. I called it Mova, which from Ukrainian translated means the language. I'm Ukrainian. And I decided, okay, if I'm building the programming language, I should define the scope from the start, what I want to build, because if you're building a programming language, you can go forever, actually, because you have to maintain it, you have to build like core API and stuff like that. So I thought, okay, I have to put some limits already. And I decided, okay, let it be the plain script, so I don't have classes and functions. You cannot define that in your language, in this language. It will be basically, imagine the main method in Java, so everything that is happening inside that main method is our code. There will be expressions, quite complex and nested expressions. There will be string operations supported, so you can, basically string operations is appending one string to another in different order, or reversing a string. You can also do conditional blocks, nested conditions. You can have loops. You can output things to the console, so it's very rewarding. It actually shows that something is happening in the language. And you can also use the program arguments, which is, I thought is useful if you want to calculate something dynamically. And comments are also handy, so I added possibility to have comments in the language. Just to give you a taste of the language, this is the syntax that I had in mind. These are actually real examples I was using for testing. So you can see there are some quite big expressions. Okay, you can use plus minus as a word. You can use symbols. You can assign things to a variable. And you can increment, decrement a value. You can also, as you see string operations, you can reverse a string. You can append it like prefix or suffix or whatever. And then you can have conditional blocks. They also can be nested. There can be a false branch if condition doesn't match, or optional. And there are also loops. In my internal terminology, there are two types of loops. So it's condition-based loops and expression-based loops. The condition is first one that you can see is a condition-based loop. So until that condition is true, do something. And the other examples are do this amount of times. And this amount of types is actually calculated by some expression. It can be anything. It can be even a decimal value. So decimal is kind of a double in my language. And it can be 2.9 times, and then it will round it up to 3 times. I thought it's fun, so let's do that. And you can have program arguments, how you use them. You say arg, and then you add index to it, and if that argument with this index doesn't exist, then it will fail, of course. I didn't really care a lot about error handling and stuff like that. I was really having fun building the language itself. And how you can output things to the console. You can say show, print, output, and then basically any kind of expression, any variable, and it will just print something in the terminal. And these are the 4 ways that I support the comments in the language, so more Java-like style or more Python-like style. And also I decided to introduce 2 types of comments for my MOVA language, note and comment. Okay, time to define some grammar. Once I had all this in mind, we didn't do any coding or any configuration just yet, but I was thinking, okay, which tools can I use to actually build these grammar rules? And of course, I came across ANTLR. It's a very powerful tool. What does it do? You give it some configurations, and it will provide you auto-generated code that basically it will generate for you a lexer, a parser, a parse tree, so abstract syntax tree of your language. Basically, all your program text will be broken down into small pieces, and you can see how it recognizes each piece. And it will generate some structures for you also that you can use to walk this parse tree. So you don't have to do a lot. You can only configure it, and if you do it right, then you can easily process it later. And I can show you in my project, I have a really nice plugin for IntelliJ for ANTLR, and I have just these 2 configurations. It can be 1 file, but I have 2. And if you have a plugin installed, you can say generate ANTLR recognizer, which will generate this code. It can be done when you ask ANTLR to do it, or it can be also done when you save. Depends on how you configure it. And then you also say configure ANTLR, and then you can say specify where you want to see that generated code. And you can specify the package where you want to put it, and you can also tell it, okay, generate listeners for me or generate visitors. So these are 2 approaches that you can use to walk that parse tree that you generate. And in my case, I was only interested in visitors. All right. Lexer and parser. So these 2 files that you have seen, these are 2 configurations. Based on these configurations, lexer and parser will be generated by ANTLR. Lexer is basically how you configure your vocabulary. So you have some words, and then the ways how you can express this word in the language. So in my case, there will be a lot of things, right? And parser is basically the rules how you will be putting these words together, how you exactly combine them to make something sensible. And you can use things like, this is my lexer configuration, and this is my parser configuration. They are in 2 separate files. It can be 1 file, but I thought it is cleaner to split them. So in lexer, I have words that, okay, this is for empty spaces. You can immediately ask ANTLR to skip the empty spaces, so it doesn't analyze them. There are other commands that ANTLR supports, but I didn't need a lot of them. And you see, I have all these words that the language will need, and then multiple ways to define it. You can use way more advanced regular expressions to do it, or if you're like me, you can use like that. And then you can also use fragments, which will not be evaluated as separate rules on their own, but it is nice to have these reusable pieces of rules that you can then digit. You can use in integer and decimal, for example. So I have these fragments as well. So you can have recursion as well, and as well in parser rules, I'm using that recursion a lot. Let me show you. So this is my parser rules. Here I'm using the lexer rules that I have defined in another file, and then I have a rule for each thing. So for expression, for assigning a variable, a value to a variable, to outputting things, and then I have the main, the whole program rule that will be then containing multiple valid structures, for example, and I match it against end of file. It's the ANTLR defined thing. And it is really nice to do it because if ANTLR doesn't recognize something in the middle, it will not analyze to the end if you don't add it. But if you say, okay, my whole program and match it against the end of file, then it will actually analyze the whole thing. And if something is wrong, it will give you an error, so you can easily see what's wrong. And yeah, you can see that I'm going from bottom up. I have valid structures. Valid structure can be a common, conditional, loop, or more valid structures. And then for each of them, I see, you see I have a separate rule. Common can be assignment, decrement, etc. A very important thing that I also use in many rules is all kinds of expression. It can be expression, a result of incrementing, decrementing a value, etc. Expression itself can be arithmetic expression or string operation. And here you see in expression, I actually care about priorities. Multiply, divide goes first, and then plus minus, then string operations, and I also have parentheses here. So by using this parenthesis, here I'm actually like nesting this expression in this one, so it will go one level deeper, and it is important to the things that have bigger priority, they go level deeper because you will be analyzing or walking this tree from the bottom up and processing it this way. Value can also be an expression, and value can be an argument that your program accepts, or a verb. Identifier is a variable defined in the program. And then I have three types in my language, which is integer, decimal, and string. So I also have this little graph where I show what I have just showed you in the rules. So I have a tree. So my rules form a tree. And also for expression. Okay, now I can show you what this IntelliJ plugin allows you to do when you test it. So I have the whole program rule, and I can test it by saying, test this rule. Okay. You see that it immediately generates the parse tree. Actually, it gives you a really nice possibility to visualize it. And if it becomes a bigger program, of course, it will be huge. But you can see that something is recognized as a valid structure, then I have dot, because all my sentences in a human language, they end with a dot, okay? Then I have another valid structure, and then these are recognized as command. This one is assignment, assigning something to a variable, and this is output. And then you can see immediately here if something is recognized wrong. And all we did so far is just these tiny configurations. The rest ANTLR did for us. And this is really nice. All right, I was mentioning about listeners and visitors. So when you ask, ANTLR generates these structures for you. These are two different approaches, and I was looking up what are the benefits of each, and of course, there is some benefit to use visitors and some benefit to use listeners. For example, if you use visitors, you have more control over how exactly what branches in which time you call. So you can say, visit this expression from a condition, for example. If you use listeners, then ANTLR will have a default walker for you that will decide, and you have less control on what you call when. And also there is another difference that has to do with the call stock. So if you use visitors, there is a possibility that you might overflow because it will go deeper and deeper into visit methods. But if you use listeners, it is managed differently, so you will not have this problem. I was choosing visitors, but I did not have any Stack Overflow problems, even though I had potential for it. I had a lot of recursive nested things. But it was just easier to start with this approach. So what did ANTLR generate from me? Let's take a look. I asked ANTLR to generate it in this package. So it becomes part of your source code. And it generated all these things for me, but I really care about this. So this is the interface of visitor, which has every node of your language, of your rules. With, it has all these methods here. And it also has the class that gives the default implementations. So you don't have to implement the whole interface in one go. You can implement it you can actually extend this class and you can implement different areas. So I ended up having 4 visitors that would be responsible for different parts. I have a main visitor, and I have, for example, expression visitor, or I have conditional loop visitor. Conditions and loops share a lot of logic, so I decided it makes sense to connect them together, and comment visitor. So I made a little diagram, so you can see it reflects the structure of my rules a little bit, but also comment visitor and conditional loop visitor, they use expression visitor, so they do call some methods when they want to visit expression. And eventually, if you do it right, your compiler, I have a compiler class which only cares about Mova program visitor, so the main root visitor, and then it knows how to spread the responsibility further in the nodes in other visitors. So yeah, I have visit valid structure, and then based on that, it will be visiting different things, and then I have all these methods implemented in these visitors. Okay. What can I do with this now? I can, if I was having an ambition to do something more serious or more serious language, I would maybe want to create another abstract syntax tree based on this one that ANTLR provides, because maybe I want to add some extra information, maybe related to the domain or to something else. But in my case, I already had enough of what ANTLR could provide, so I could immediately generate the bytecode using these visitors. So I can immediately already call my bytecode generator. I have this bytecode generator class that does all the dirty work about generating the bytecode. So, bytecoding time. I was using ASM to generate the bytecode. It's a very powerful tool. It's not very user-friendly if you don't know how the JVM works internally. It is hard to understand, about the same as just reading this bytecode that we saw in the first screenshot. So you really need to understand how it works. Luckily, they have a really good guide, which takes like 200 pages. But what's nice about it is that it actually explains the internals of JVM, and next to it, it also explains how you can use the ASM to generate things like that. ASM can actually both generate and also parse the compiled classes. It can do both together to reflect some changes in the real time, for example. It is used by many software products, to name a few. Many compilers use it. ByteBuddy is a tool that is built on top of ASM, which can provide you a nicer API if you don't want to worry about these internals of JVM, etc. And ByteBuddy is used in Mockito, for example. So there are also 2 approaches you can use ASM. So I will be only talking about generating the bytecode. I was not interested in parsing classes. And for that, I could use also 2 approaches similar as with ANTLR, listeners and visitors. And basically, object-based one is having the whole tree of your whole class structure. So the class and the methods inside and the code inside the methods form kind of a tree as well. And all this tree is held in memory if you use object-based approach. And it is easier to use it, but it also makes it a bit slower. And if you use listeners, then 1 element will be available at a time. So my plan for generating the bytecode, what did I have in mind? You need to create a class writer. Class writer is the place where everything starts when you want to generate the bytecode. Then you start a class definition. So it will be the only one class that I have. Then start main method definition, because everything I do will be happening inside of this main method. And actually, it was surprising for me a bit that everything is still in Java-like style, like even underneath it's still method and main method. And then you can have a reference to method visitor when you create this method, like start the method definition. And here you can already do anything you want. You can generate the full method body, you can generate all your program. This is where all the fun happens. In the end, afterwards, you will finish the main method definition, you will finish the class definition, and then you can write the resulting byte array into a class file, and then this one you can already run with a Java command from a terminal. So that was my plan. So I can show you also in the project. So my bytecode generator. In the start, I'm creating a class writer. So this one. And then I have an init method where I start the class definition. So it's a public class that will be extending from object. Then I get the method visitor by saying visit method. It will be a public static method, and then it will be a main method. And then this is to describe what the method accepts and what the method returns. I will touch this later. Then you say method visitor visit code. And then after that, you can say tell this method visitor to do all these other things that we want to do in our code. And in the very end, I have the method to cleanly close all these definitions. So I have to return from the main method. I have to do some stuff related to slots and states, which I will explain in a second. And then we tell method visitor to finish the main method definition, we finish the class definition, and then we have the resulting byte array that we can return back and write it to a class file. So exactly as I described. So that bytecode thing, before we can actually generate the bytecode, it is very important to understand a couple of things about what is happening inside of the JVM. These are not just theoretical, they're very useful practically. So you know that when you on your call stack, you have frames. When you call one method from another, you can end up in a different frame, right? And each frame, in each frame you have a state. And two very important things that I really cared about were local variable array and operand stack. And local variable array holds all these variables that you are using in this particular frame. And then in operand stack, you put everything that you need to call your operations, to call your methods. So everything that these methods accept, everything these operations want to use, they need to be taken from operand stack. So before you can actually do something, you only need to put it on operand stack, and they will be returning it back also to the operand stack. And for example, you want to create a variable. Imagine we're in Java in the main method, and you see in local variables we already have index 0. It is busy with array of strings because main method accepts array of strings. We want to create a variable. We cannot do immediately putting stuff in local variables. We first need to put it into operand stack. LDC is the bytecode operation that you can use for it. It has to do something with a dynamically calculated constant value. And only after that, you can use commands like istore, dstore, astore, then index in which you want to put it in local variables. So in this case, it will be 1. So why is it istore, dstore, astore? So first letter stands for a type, and you need to know which type exactly you're dealing with. I stands for integer, D for double, A is a type reference, and there are more. There are lstore, etc. You have to always know what types you're dealing with. Otherwise, it won't work. Okay, using this, you can put it here. If you want to use this variable, you will first need to load it on top of operand stack. Using this operations load, and also depending on type, you will add a letter in front of it, and you will have to specify the index of a variable which you want to load there. Yeah, so now we see it's here. Okay, everything is using the operand stack, and there are operations, for example, to add two numeric values together, right? We have a stack that you see on the left, and we have two values on the top. One is integer, and the next one is double. Integer takes 1 slot, but double takes 2 slots, both in operand stack and in local variables. And long values also take 2 slots. So these are the weirdos. But in my language, I was only dealing with double. So double is a good example to illustrate this. So you want to add these 2 values. You cannot use iadd, integer add, because integer add can only deal with 2 slots at a time. It will fail. You cannot use dadd, because dadd wants to use 4 slots. So you need to first convert I to d, is integer to double, so you'll have the state that you see on the right, and only after that you can use dadd, which will add 2 double values. You have to always keep in mind what types you're dealing with, and only then you can have the proper operation. And of course you don't have to deal with the stack as is all the time. You can do things to change the state of the stack. For example, you can swap the values around, or you can duplicate the value. For example, one of your methods, you call a method, it uses this value, but it also pops the value from the stack. You want to use it again in next call. Then probably it's nice to duplicate it first before you call that first method, right? And also, if you use swap and dup, you can also pop value manually. If you use these things, they will only deal with 1 slot values again. So if you want to deal with 2 slots, then you have to play a bit. And if you have 2 slots versus 1 slot, and you want to swap them around, these are the combinations of operations that can do that. If you Here in this case, we want to swap 2 slot value with 1 slot value. We will have to duplicate 2 first slots on position x1, which will go after the next one, and then pop 2 first values from the stack, and it will end up reversed. And in my code, I can show you that it is exactly 1-to-1 doing what I'm showing here. So as I said, if I have a decimal, then I have to play. Otherwise, I can just use regular opcode swap. In ASM, it's called exactly the same. And then I have these methods if I have weird situations where I will be swapping 1 slot with 2 slots, for example, 2 slots with 2 slots, and yeah, exactly these operations that I have told you about. Another important thing that you need to know if you want to generate the bytecode is there are type descriptors and method descriptors. So type descriptors are the ways to describe the type internally for JVM. And the capital letter stands for primitive types. So you can see double, you can see Z, which is Boolean, integer, etc. And if you have a reference, then it will be specified with slashes. In the front, you'll have capital L, and in the end, you have semicolon. If it is an array, it will start with a square bracket. If it is a two-dimensional array, as you see on the bottom, it will have 2 of them. And you can see, for example, it's a 2-dimensional array of object. And then method descriptors are using type descriptors, and method descriptors are meant to specify what types method accepts and what it returns. So what is inside the parentheses on the right, you can see that these are the types that it accepts. In the first example, it's integer float and returns v. V stands for void, so it returns nothing. And yeah, you can see the next example, for example, accepts object and returns integer, etc. This way you can call any core Java API methods, actually, which I was doing in my code as well. Let me show you an example. So you can ask ASM to provide you type descriptors. For example, type, double type, get descriptor. I have this here to just show how it looks. So you have a string dot replace method. So you can say method visitor, visit method, blah, blah, blah. And you specify the owner, the name, and then this expects a char sequence, another char sequence, and it returns a string. So this is how you can use and you can easily call any core Java API. Okay, there are some other things that are important for a compiler. One of them is to keep track of all the variables mapped to their indexes, because in the bytecode there is no variable names. There's actually indexes that you can use. And in your compiler, you know about the names. You want to reuse these variables by names, so you have to keep this mapping of name to index. Another thing to keep track of is your type stack. So you have to locally keep this stack in the same state as you know that it should be in the JVM side, because otherwise you will not know what to do with these two values. And for example, on top of your operand stack, you have two values, you want to do some operation on them, for example, add them, and it will be a string and an integer. So you will have to define some logic to know which type wins. And in my case, I know if I have a string operation, and if I have a string and something else, then I will have to convert the other thing to string and do the string operation. If I have an arithmetic operation, and I have a string or an integer, I actually convert things to double, and then I can do something in double, because double will actually be easier to calculate things. And I'm always trying to be guessing what the user wants, what the program actually meant, what type is it supposed to be. I'm trying to be a bit of JavaScript. And as I mentioned, I don't have any error handling. So if it fails, it fails. OK, and there was also another important thing to mention, that as I mentioned before, there are frames, and when you use conditions and loops, you do a lot of jumps. And when I came to this part, it became tricky, because when you jump, you may end up with a new state, and actually the JVM wants to know if you want to keep the state from the previous frame, or you want to reset the state, etc. And it started failing, so I figured that you actually have to keep count on all your slots, maximum amount of slots for local variables and operand stack that you're going to use for your whole program. And you have to tell JVM this amount, but if it is tricky to calculate, you can ask ASM to calculate it for you. And same goes for frames. JVM wants to know which local variables, which state you want to take over to the next frame. And if it is tricky to calculate, then ASM can also do this for you. So I have this, when I create a class writer, I can ask it to compute frames, so this will calculate the states. I can also ask it to calculate max, which will calculate the number of slots in local variables and in operand stack in your whole method or program. And in the end, when I finish the main method definition, I have to call this thing. And here I would usually provide this number of slots for operand stack and local variables. But because I did not calculate them myself, I provide zeros, and ASM calculates it for me. But I must call this method, otherwise it will not work. And basically, you need to do this when you finish every method. But I only have one. OK, and also, this is on the right to illustrate how I was making the conditions. So I have three labels here: true label, false label, and end label. TL, FL, EL. These labels can be named whatever you wish, and they can be placed wherever you want. And first line is if GT, which means if the value on top of operand stack is greater than 0. It can be any other operation. There are more conditions like that. It's just to illustrate. So if this condition is true, go to true label. True label is where you run some code, and then you go to end label, so you finish it. And if you didn't go to true label before, if you went to the next line, you'll immediately jump to false label. And then on the false label, you do some other code, optionally, and you also go to the end label in the end. So here I have the implementation the same way. So I have three labels. I have to create them beforehand, and then when I want to place a label, I set visit label, some true branch, false branch optionally, and condition end. And here I also have if greater than 0, then we go to true branch. Otherwise, we will go to, if we have a false branch, then we'll go to the false branch. Otherwise, we'll go to the end. Very similar approach I have to do with loops. It's just different order of jumps and different order of calling things, but basically the similar approach for organizing loops. Error messages. So there are actually 2 levels of error messages when I was trying to generate the bytecode. One is whatever you generate, it makes no sense at all. And then it will give you something like this. It will give you a very nice descriptive error message, which is really nice because you can see which line exactly, so which number of operation it failed exactly. In this case, it tells you which one is swap operation. It tells the reason, so you're trying to reference double second, so second half of double value. It references it as something that is one slot thing. And it also gives you the state of your local variables and state of your operand stack at the time of failure. So you can actually see what exactly went wrong. And here you can see that on the top of your stack you have integer, double second, right? So you're using swap operation. It expects one slot thing, it takes double second, and it fails because it cannot deal with that. So another level of error is when your bytecode actually does make sense, but it behaves different, it behaves weird, so you can actually decompile it to Java and take a look what it thinks of your code, because then it is easier to visualize what went wrong exactly. Maybe something in the logic or something in the order of things. Okay, let's take a look at some Java example. Very simple program, integer a equals 1 + 1, and then we print this. If we compile this program, we will see, decompile it back to Java, we will see this. So we see 2 instead of 1 + 1. So when Java compiler works, it does some optimizations. So this 1 + 1 was not done in the bytecode itself, it was done on the compilation. And inside of the bytecode, there is no I-add or anything like this. But if we do the same in my code, and if I compile it, because I already directed my compiler to this file, it will say 2, okay? And if we take a look at the class and decompile it back to Java, so it will show you 1 + 1, and it will be actually, you can see that everything that is happening not in the compiler, it's not calculated in the compiler, it is calculated in the bytecode. And I have actually a lot of things that if we decompile it, we can take a look. You will never see Java do that. So it was really nice to see that what it thinks of my bytecode. Okay, and now it is demo time, so I prepared 2 little demos. Let's try them out. So I will paste it here. So the first one is string. We assign value jfall is to some variable called string. Okay. Then we accept some value. It will be an integer value. We will do this amount of times append super to this string. And if this value is bigger than 3, we will append awesome. And otherwise, we will append just nice. And then we'll show it in the console. So if we compile it now, and we say 0, then jfall is nice. Okay. Then we provide 3. It will say 3 times super, nice, okay. And now 4. It will say super, super, super awesome. Okay. Thank you. And another one. I tried to make examples where I could use my whole stack of the language, whole possibilities of the language. Another one, we accept some value. It will be already considered as a string. And if it is high, we will show something. If it is by, we will show something else. And then we show something more. By the way, if you want to combine 2 things in one block, you can use the word also. I made this possibility, so if you have a condition, for example, you can run several commands on that condition, and only in the end you put this dot as in a sentence. This is exactly, all this program text is written without any programming symbols, it's just a human sentence. If we compile it, and if we run it, we say hi, it will say hello GFall. And if we say bye, it will say bye-bye GFall, see you next time. All right. If I had an ambition to make this language more serious, if I wanted to develop it more, what would I do? I would do these compiler optimizations that I told you about, see how far I can actually optimize things, and maybe some things cannot be pre-calculated already in compiler, but some of them can, so this is another interesting task to actually do this. Maybe a possibility to create functions in the language and call them, create the core language API, because without it the language is very limited, and you can keep on building this core language API using Java underneath until you have enough of the base of your own language, which you can reuse to build more API. This is basically what they do with Kotlin. Yeah, and you name it, you can add more things, but I don't have an ambition to continue. It would be future steps. If you're curious, you can take a look at GitHub repository is open. Feel free to take a look. You feel free to contact me on Twitter. And yeah, I think we have some time for questions. Thank you. Yeah. Sorry, can you? Yeah. You, of course, you cannot call my stuff from Java, but I can call Java stuff from my language. So I'm building it. Yeah, basically, it is built on top of JVM, which is inside is fully Java. Yeah, but I cannot call my stuff from anywhere else. Anyone? Yeah.
What's the Easter egg?
It's not super exciting, but I can show you. It is, I told you that I come from Ukraine, right? Yeah, it gives the proper output. Anyone? Sorry, it means, so I said glory to Ukraine, and it replies glory to heroes. Yeah. What
is the name of your language?
Mova. It means the language in Ukrainian. Yeah. Yep, okay, if you have more questions, you can come to me after the session, or I'll be whole day here, so you can reach out to me. We'll be around Xebia booth, so yeah, see you around. Thank you.